Well, good morning. This is 11:35. Sorry, 5 minutes late getting started, but there was no student in the room, so I went and took care of a couple of other things while I had a minute or two, but it took longer than I thought. But I'm the only one in the room still, and so we're going to pick up from the current slide. This is Math 237 Linear Algebra, and we'll pick up from where we left off last time, which was, and I need the light on. I thought it was brighter in here than this. Okay. We're in Chapter 3, should be finishing it today. Determinants. 3.4 is applications of determinants. And we were at the test for coplanar points in space. Remember, we did this for collinear points in the plane. Same type deal, except it's three-dimensional. So what if you had 4 points, and they're given as, well, no, I'll make the announcements after someone comes in. I don't want to make announcements to an empty room because I don't know if anyone's going to listen to this anyway. So anyway, here we have our 4 points in a plane, in space. So they're three-dimensional points, x1, y1, z1, x2, y2, z2, x3, y3, z3, very creative in the way they number these things, and x4, y4, z4. Okay. 4 points in a plane. 4 points in space. Now, these are coplanar. They're all in one plane if and only if. Okay? Sometimes this symbol and sometimes IFF. If and only if the determinant of those dimensions, and that would be x1, y1, z1, 1, x2, y2, z2, 1, x3, y3, z3, 1, and x4, y4, z4, 1. If that determinant is 0, they're all in one plane. Okay? Now, they may even be on one line. Probably not, but they could be. Still, the determinant would be 0 because that line is in a plane. But if they're of course, any three of them will be in a plane. Three points defines a plane. But if the fourth point is not in that plane, then the determinant will not be 0. If that fourth point is in that same plane, then the determinant will be 0. Okay? Now, an adaptation of that is, of that test is the determinant form of the equation of a plane passing through 3 points in space. So in other words, if you have 3 points in space, let's take the first 3. I'm going to do this one a different color because this is a different deal here. Let's do it purple. If these 3 points are they make a plane, like I said, any 3 points make a plane, so let's take those 3. And then we do a determinant a lot like this one, only not quite. We do the determinant of x, y, z1, x1, y1, z1, 1, x2, y2, z2, 1, and x3, y3, z3, 1. Do that determinant and set it equal to 0. Then we'll come up with an equation for the plane that contains those 3 points. Because you see, now we'll have a variable in there, okay? And that's how we'll come up with the equation of the plane. So let's do example 8 using this second principle We'll erase what we've got there and also go back to black. Okay? Find the equation of the plane passing through these 3 points, 0, 1, 0. That's on the y-axis. -1, 3, 2. Okay, that's somewhere out in a different quadrant, octant, okay, and -2, 0, 1. That's somewhere on the XZ plane. Okay? So, we want the equation of a plane that passes through those 3 points. Well, we'll set up our determinant here, and the top row is always X, Y, Z, 1. Okay? The next row would be your first point, 0, 1, 0, 1, and -1, 3, 2, 1, -2, 0, 1, 1. Okay, and we want that determinant to be 0 to get an equation of a plane. Okay, now, again, usually a good idea to pick a row or column with the most zeros in it. Well, that looks like it's just going to be this row, second row, okay? And let's just go with the second column too. Now that position here, right here, is a positive position, plus, minus, plus, plus, minus, plus. It's a positive position. It's on the diagonal too. It's always plus, okay? So that's going to be, the determinant of this will be a plus, and it's a 1. So it's the determinant of what's left over, okay? So that's going to be 1 times, and the determinant of what's left over is this, X, Z1, -1, 2, 1, and -2, 1, 1. Okay? Now, to do that determinant, we're just going to repeat the first 2 columns. Okay, X, -1, -2, and Z, 2, 1. And we'll do our, it's not really a determinant, we'll do our diagonal, and that will be 2X, gotta line up my things right, -2Z, and we want this equal to 0, okay, -1, okay, now I'm going to take those lines off because they're really ugly and are hard to see. And now let's do our up diagonals, which are the negatives. And the negative of that one would be a +4, because it is a minus, but going up changes the sign. That would be a -X, and this will be a +Z, and that's equal to 0. We know that, okay? So, let's see what we get here. X, because X minus 2X minus X, minus Z, plus 3 is equal to 0. Yeah. So, that's a little unsatisfying because you only have one equation, okay, but 2 unknowns. So let's write it as X minus Z is equal to -3. Okay. not the best way to go on this. Let's back off. Because we lost our y variable. I worried about that when I did it because it looked like we were going to lose it. I thought it would be pretty obvious how to get it back. It's not. So let's go back and do our whole determinant. Let's not take anything out. But what we can do is eliminate this 1 right here. Okay? If we can get rid of that 1, I think we'll be in good shape, because then we'll only have a 1 here. Okay, how do we get rid of that is and in the rows that doesn't help us much, but in the columns it's pretty easy to do. We'll subtract, we're going to keep this one and subtract, how would we do that? Column, this will be column 2 minus column 4. That will do it. Column 2 minus column 4. Okay. Now, elementary column operations, as long as you're doing stuff like this, it doesn't change the determinant. Okay. So this will be a x 0 minus 1 negative 2, just like before. This will be a y minus 1, because you're subtracting column 4 from column 2, 0, because 1 minus 1 is 0, 2, 3 minus 1 is that, and minus 1. 0 minus 1 is minus 1. Leave the next two alone, z, 0, 2, 1, and 1, 1, 1, 1. And that's still equal to 0. The determinant is still equal to 0 because we didn't change any rows, columns, or multiply by any constant, or divide by any constant. So we didn't change the determinant just by doing that elementary operation, adding a multiple of one row to another row. Okay. So at this point, then we can eliminate this row and that column. Okay. This keeps our x's, y's, and z's in place. Okay, but we need to know the sign of this position. Plus, minus, plus, minus, plus. So it's still a plus. Okay, so the determinant of that is a 1, and we'll do the rest of them. And since it is a 3 by 3, let's go on and do it again. X minus 1 minus 2, and y minus 1, 2, 1. Okay, we're going to do this. I'm going to take out this line because it might be confusing. Maybe all this is confusing, but we're just doing that, what remains of our thing. So the first diagonal down is going to be this, that, that. Okay, doesn't look like diagonal, but that's all you got left. So it's going down that way, and that would be a 2x. Okay. Now the next one is this one, that one, that one. Okay, and that's a minus 4y plus 4, because you got y minus 1 times a negative 4. So that was minus 4y plus 4. Okay, and then this down diagonal is that one. Okay, and that is minus z. Okay, now our up diagonals, be careful here. It's this one. Let me erase the others so it'll give us a little more clarity here. All right, our up diagonal, which of course is going to be the negative direction, is that one, and that was a minus 4z, but with the negative it becomes a plus 4z. Okay, next up diagonal would be that one, and would have been a minus 2x, so it becomes a plus 2x. And then the final one was this one, which would have been a minus 1 times that is plus 1, so it's just plus y minus 1. Okay. Now combine your x's and y's, and this is equal to 0. Combine your x's, y's, and z's. So here we have 4x. You got minus 4y plus y is minus 3y. That's those two. And here you have a plus 3z from those two. And let's go on and just leave it on this side and do plus 3 is equal to 0. That's an equation of a plane. Okay? Now, do they leave it like that? I screwed something up. The 4x minus 3y is fine. I messed up the z's somehow here. See, our down z was a minus z, and the up z let's see if I got my matrix right. X, y minus 1, z, 1. 0, 0, 0, 1. Minus 1, 2, 2, 1. And a minus 2, minus 1, 1, 1. Now those look okay. Ah! Well, I don't think it mattered any. That should have been a minus 1 there. Okay. I'm not quite seeing it, but let me try it again. That's a 2x, that was right. A 2, let's see. No, that's right. All right. I'm going to take off my lines again because I'm having trouble keeping it straight. Okay. Try them this again this way. This one is this, that, and that. That's a 2x. That, and that. That's a minus 4y plus 4. Got it? And then that's a, I did use it. That's a plus z. Yeah, that's it. Now that, yeah, that gives us plus 5z. That minus sign I left off, that's the one that did it. Up right there. Okay. That's equal to 0, or the other way you could write it is 4x minus 3y plus 5z is equal to negative 3. Subtract 3 from both sides. And that gives you that. Okay. So, one side, blew it. All right, then there's a linear algebra applied. According to Kepler's first law of planetary motion, the orbits of the planets are ellipses with the sun at one focus of the ellipse. The general equation for the conic section such an ellipse is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. To determine the equation of the orbit of a planet, the astronomer can find coordinates of the planet along its orbit at 5 different points. Then they can do the same thing we just did and determine the equation of that planet's orbit, the plane in which that planet lives. That looks like a big pain in the neck. Not only just doing a 6x6 matrix, determinant of that, but then in addition to that, you've got to, even before you can do it, you've got to plot, 5 points for the thing. How in the world do you plot points when the whole solar system is drifting out there in space? There's no coordinate system to put it under. But they know how to do that kind of stuff to a reasonable amount of accuracy and get it done. And that was the last example, last object in 3.4. So homework exercises here. Any of the odds 1 through 7, they all are at Calc Chat. Also, their answers in the back of the book. So if you can't get the answer in the back of the book, go to Calc Chat, or see if you can figure out how to get that answer. If you can't, go to Calc Chat, and you'll see worked out solutions for those odd number exercises. Number 9 is a proof. Probably pretty good to look at that too. 11 is a proof. Not bad to look at that one. Then do 13 is not a proof, but well, it's illustrating the formula you did in 11 using the data in 13. 15 is a proof. Then any of the odds 17 to 29 using Kramer's rule. Then any of the either 31 or 33 using Kramer's rule. 35 is using Kramer's rule. Then finding area of a triangle, 37 and or 39. All at Calc Chat. All these odds are at Calc Chat. 49 or 43, those are at Calc Chat. 45 or 47, those are at Calc Chat. Any 49 or 51 is at Calc Chat. 51 or 55 is at Calc Chat. 57 or 59 is at Calc Chat. 61 should be at Calc Chat. Then there's an applied problem 63. You're certainly welcome to try to tackle that as well. And that ends Chapter 3. So if you need more practice, you can do on the review exercises. Again, odd number answers are in the back. They may even have even answers in the back for review exercises. I don't know. But at Calc Chat, it's still odd number exercises there. So any of the odds 1 through 17, any of the odds 19 to either 19 or 21. This is only if you think you need some extra practice. 23, 25, 27, all should be at Calc Chat. Either 29 or 31 should both be at Calc Chat. 33 or 35 should be at Calc Chat. 37 to 41, those should all be at Calc Chat. Odds 37 to 41. 43 should be at Calc Chat. 45 should be at Calc Chat. 47 at Calc Chat. Either 49 or 51 at Calc Chat. 53 is a writing problem if you want to take a look at that. So is 55. And I think, they continue. 57 should be at Calc Chat. 59 or 61 should be at Calc Chat. 63 should be at Calc Chat. 65, 67, 69, all at Calc Chat. 71 should be at Calc Chat. There's a couple true false, 73 and or 75. Okay? And they should be at Calc Chat as well. Okay? There's a project here on stochastic matrices. If you want to look at that, there's the Cayley-Hamilton theory. We mentioned, I think, both of those in the chapter, if you want to take a look at those. There's a chapters 1 through 3 cumulative test. If you wanted to take a look at those, their odd answers are in the back at Calc Chat as well. Let's at least talk about vector spaces. This is chapter 4. We're not going to have time to get very far in it. We've only got today. No, we got Thursday. So today and Thursday. And let's get as far as we can. And if possible, if we can get enough covered, then I might give you a very short, it's going to be almost more like a quiz, but that will be the last test then, is chapter 4 test. I didn't bring up my watch, so I don't know what time it is, but I think we've got time. Let's start chapter 4. All right. Chapter 4, the title of it is Vector Spaces, and 4.1 is Vectors in R superscript N. What do we mean by that? Okay, so let's clear the slide here and start talking about vector spaces and vectors in the plane. In physics and engineering, a vector is characterized by two quantities, length and direction, represented by a directed line segment. This chapter you'll see that these are only two special types of vectors. Their geometric representations can help you understand the more general definition of a vector. So here's the general geometric definition. Vector in the plane is represented by directed line segment. Okay? Now, every word of that is important. Okay? Directed means now we're talking about something that has a direction. When we're talking about regular scalar numbers, they're just numbers, you know. They don't have a direction associated with them. You might say a plus or minus sign gives a little bit, but that's only if you're talking about along an axis or something like that. Then, yeah, that gives a little bit of direction. But when we're talking about a directed line segment, we're saying the direction of that line segment is important. Now, the second word there is line. That just means it's straight, okay, a straight line. So that's not really as important. But then two, a line, by definition, goes infinitely in two directions, okay? But always in a straight line, okay? There is another term they call a ray, which has one fixed point, but the other end goes indefinitely in that one direction. Or you can have two fixed points, your initial point and your terminal point. That then is a line segment. It has a fixed length and, of course, being directed a fixed direction. The initial point, the standard form, has the initial point at the origin and the terminal point somewhere in the XY plane. So actually I'm going to go to this, and we'll have this as our initial point in the center, and the terminal point up here somewhere, right there. That'd be the terminal point, okay? So this is initial point, 0, 0. Terminal point up here, x1, y1, okay? Now, if it's a point, we put it in parentheses, okay? This then would be the vector. They give it the name x. I really don't like using x because you think of that as a horizontal axis. In this case, well, I really don't like it because they gave the first component as x1. I wish they'd have called it v or u or w or anything other than x or y. But they called it x, but it has nothing to do with the x-axis. Okay, that's just vector x. Okay? And the arrow on the vector is always pointed away from the initial point directly toward the terminal point. Okay? Now, when the initial point is the origin, and that's our standard position for it, then the components of the vector are the same as the coordinates of your terminal point. Okay? The coordinates of the terminal point, those indicate a point, x1, y1. They become components of the vector x. Okay? Now, that same ordered pair is used to represent the terminal point of the vector, but it also can be the components of the vector. Now, here's the thing that kind of drives me a little nuts. Okay? I'm currently teaching pre-calculus algebra from a book, actually pre-calculus algebra and pre-calculus trig, from a book authored by Ron Larson, the same author we have here. Okay? I'm teaching Calculus 1, Calculus 2, and Calculus 3 from another book authored by Ron Larson. And in both of those books, when he's referring to a vector, he puts it in angle brackets. And then he puts the coordinates of, the components of those vectors, x1, y1, in the angle brackets. Okay? This book, however, authored by the same guy, he puts them in parentheses. So you have to pick up by context whether you're talking about the point. This is a point right there, x, y, actually the point Q, let's say. This is the vector, and he still labels it the same way, x1, y1. And for the life of me, because I'm so used to putting angle brackets, you'll find me still putting angle brackets every now and then. In his text, however, in this text, he uses parentheses. And you have to go by context. If he's referring to a vector, those are components. If he's referring to a point, those are coordinates. Okay? And the trouble is they're the same numbers quite often. Okay? Same ordered pair can either represent the vector or represent the point, terminal point. Okay? Now, another little mention here. If you have one vector in the space u1, u2, and another vector, I believe it's v, vector v is v1, v2. These are the components of the vectors. Both of those are components because these are vectors you're talking about here. Well, these two vectors are equal to each other if and only if the first components are exactly the same and the second components are exactly the same. Okay? That is required. U1 must equal exactly the same as V1, and U2 must be exactly the same as V2. All right. So let's move on to example 1. Okay. Now, always seems to hit just about this time. This room is cold, and it's just making my head just close up on itself. So if it sounds like I'm talking from inside a drum, I feel like I'm talking from inside a drum. Head's hurting, all that kind of stuff, and so I apologize if the sound is not as good. You may not be able to tell any difference, but I sure feel a difference from what it was earlier. So here's example 1, bottom of page 146. Here is a vector u, and that vector is 2, 3. So you go horizontal 2, up 3, and here would be the vector 2, 3. U is the vector 2, 3. 2 to the right, 3 up. To represent U, draw a directed line segment from the origin to the point 2, 3 as shown. So this point is 2, 3, and the vector going to that, so this point is 2, 3, the vector is also 2, 3. These are coordinates of a point, components of a vector. Okay. Now, to represent the vector v, negative 1, 2, I'll do this in a different color. How about purple? So v is negative 1, 2. That would be left y up 2. So here would be vector v. Negative 1, 2. Okay? And this would, of course, be point, negative 1, 2. Drawn from the origin. We call that sort of standard position. Okay? And that's all there is to it. I'm sorry. That's all example one was, is draw those two vectors, represent the two. And we did. Okay? Okay, good deal. Did you finish?
Yeah. Did you want to scratch everything?
I'm sorry?
Did you want to scratch everything?
It's up to you. If I find something wrong on the test, but you got it right on scratch, I can give you credit for it, or at least moving in the right direction there, I can get partial credit. So it's up to you.
I didn't do all of them.
Okay, that's fine, but yeah, it's up to you. You get to turn it in or not. Okay, I'll take it. Thanks. Sorry about that. A student from the last class was finishing. No, my first class was doing a test. She missed class today, so she was making it up. Okay, that was example 1. And that was page 146. Moving to 147. Let's go back to the clean slide. And one basic vector operation is vector addition. Now, I really do. I'm going to pause because I really need to keep up with time now. So I'm going to pause a minute and run get my watch. I'm back. Sorry that took just a couple minutes more than I thought it would, because a student was kind of lost in the hall. I'll see how this late in the term he could be, but I had to help him find what he was looking for, but it didn't take long. But anyway, we're talking about vector addition, and to add two vectors in the plane, add their corresponding components. It's that easy, okay? So if you have a vector u, let me get back to my black here. Sorry. Felt really good out in the hall because it's warmer. As soon as I came back in the room, my head clogged up again. So here we go. If you got vector u plus some vector v, now you can represent them by in their component notation. Now remember, parentheses, when you talk about vectors, indicate components of a vector. This will be u1, u2, that's vector u. These are components, they are numbered, scalar quantities, okay? Plus, vector v would be v1, v2, and to add those two together, you get a vector, and that vector will be u1 plus v1, add the corresponding first components, x components together, comma, u2 plus v2. It's that simple, okay? That's the sum of two vectors, okay? Now, if you were doing it graphically, I'm sorry, I went the wrong direction, doing it graphically, let's just take the two that we have here. They show different ones in the book, but let's just take these two. What if we were adding those two together? Then here is 2, 1, there is negative 1, 2, 3, and there is negative 1, 2. If we're adding that, then you add the 2 and the minus 1, that would be a 1, so you're going to wind up here, and you add 3 and 2, that winds up 5, so that would be here, okay? Well, here is the sum of those two vectors there, okay? And that vector sum, u plus v, would be 2 minus 1 is 1, and 3 plus 2 is 5. You just add their components. Now, here's the thing somewhat to note. Okay? What you've basically done there, going back to my purple here, is to draw this vector v at the end of u, because you're adding them, so you do the terminal point, the initial point of v onto the terminal point of u, and then connect the initial point of u to the terminal point of v. That would then be your resultant vector there. Wonder if I should have done that in a different color too. Like maybe Carolina blue. So, yuck! My screen keeps flopping on me. There would be your resultant vector. I'll take out this one because that's sort of hard to see. So there's the resultant vector. And another thing to note there, hopefully of interest, what if you took vector v and put vector u from the initial point of u onto the terminal point of v and go up that way, and there you have another way of expressing it, which basically is saying that u plus v is the same as v plus u because they have the same resultant vector. The sum vector is the same. Now, the other thing to note about this forms what we call a parallelogram. So, graphical representation of vector addition is sometimes called the parallelogram method. Okay. Now, and the vectors u and v are any two adjacent sides. Here they're adjacent here, here they're adjacent there, here they're adjacent there, here. They're always the two adjacent sides are the individual vectors u and v. Okay? Now, there is one other vector which I have problems calling it a vector, but you have to have it. And if we had time to do the entire chapter 4, you'd see why. In fact, just a couple more sections of it, we probably will have time. It's called the zero vector. And here's the problem with the zero vector. Okay? I'm going to go back to my black here. The zero vector has, by definition, components 0, 0. Now, here's the problem that I have with the zero vector. At the very beginning, we said a vector is a directed line segment, which means directed means it has a direction, and the line segment means it has a magnitude. Well, the zero vector, and by the way, this way we refer to this is the only one we use a number for the vector. That's the zero vector. Okay? In the book, it'll be a bold 0, and the components will be non-bold zeros. Okay. Here's the problem. I count two really big major problems. First, it has no direction. The zero vector is not pointing anywhere because it has no components. The components are 0, so you're not leaving one and going to another. You're at that one point, 0. So it has no direction, and it has no magnitude. It has technically 0 magnitude. So therefore, it hardly classifies as a vector, but you have to have the zero vector because, as we see later, the title of this chapter is Vector Spaces. You have to have something representing 0 in a vector space to be a vector space, and therefore it's required that you have a zero vector. Okay. So, let's go back to the clean slide. No, that's not how we do it. Okay. Oh, okay. And let's do example 2. We don't need to do them on the graph. That's just really a big pain. Though in the book, they draw them on the graph too. So, okay, let's go back and do them on the graph. Okay, sorry. So let me clear this slide. Okay. The A part of example 2 says here is vector u is 1, 4. Vector v is 2, -2. Okay? It says find the sum of those two vectors. Well, u plus v would then be, well, there's Daniel. Finally, I've got to shoot it here. Okay. Daniel's here. All right, let me back up a moment. I didn't make any announcements originally. because there are no students in here. So let me make my announcements now. And they're pretty important because they're basically trying how we're going to term. So Thursday is the last day of class. Okay. Now that means several things, but before we even get to that, have you done the student course evaluations? No. Please do your student course evaluations. You don't have to do them now or immediately, but you can wait until you see what your final is, or you can wait till anything, but just please don't forget to do them. That's for both classes. And if they ask for any additional things like registration or a library or anything like that, please do those as well. I get feedback from you anytime we interact. Those folks don't always get feedback from you, so please do those evaluations as well. Okay. So that's beside. Now, Thursday, last day of class. It's the last day to turn in your research paper without losing points. I will accept them later, but you'll be losing points if I do. So Thursday, last day to turn them in. Get them to me today, get them to me tomorrow, get them to me by class time on Thursday. Okay. That's one thing. Also, that's when you should have all your tests in. All of your tests in by Thursday. Now, the one I gave last time, test 3, that may wind up being the final exam. I don't know how far we're going to get in chapter 4. We started it today, but and we got class on Thursday. So if we get enough, I might give you a very short, quick test on that as your final exam. But otherwise, it may be chapter 3 test will be it. Okay. Now, I will be giving back all the tests on Thursday. That means I cannot accept any tests after I give those back, because then they're out there, the answers are there, you can't do it. So I've got to have them all in. Rather have them in today, rather have them in tomorrow, but no later than the beginning of class on Thursday. Okay, that's your research paper and your test. Research paper I will accept late, the test I cannot. Okay. Now, so that's what I'll be giving back to you. You get me your research papers and all your remaining tests between now and Thursday. I'll be giving back to you all the tests that have been turned in so far. Okay. But I'll be giving those back to you. And then I'll also be giving you, if we have a test on chapter 4, I'll be giving you that. It'll be very short, very brief, but we are covering material in it now, so we may have enough that we can do a very, very quick test on that. Not going to take long. Now, let me back up a moment. Are you graduating this term? No. If any of the other students are graduating this term, you've got to get your final exam, whether it's test 3 or test 4, whichever it turns out being, into me by next Thursday. Now, that's technically when all of the tests are due, but I've got to have the graduates in by Thursday because your grades have to be in by Friday, noon on Friday. So I've got to have all your work in by Thursday, your final exam in by Thursday. For the rest of you who aren't graduating, I can't accept them as late as Monday. Monday is technically the last day of finals, but your grades don't have to be in until Wednesday at noon. So that gives me a day to grade them. So please get your final exam into me by the following Monday. Sooner is better, but no later than the following Monday. Otherwise, you'll probably get incomplete in the course until I get your stuff in. But then you have to clear that before so many weeks into the term, next term, or it becomes an F. That's done by the system, not by me. Okay, so anyway, any questions on how we're going to wrap up the term? Research papers and all previous tests have to be in by Thursday. Before that, it's better, but Thursday is the deadline. Deadline on the research paper, and that you start losing points after that. Absolute deadline on any of the tests, except maybe test 3. Because did you get test 3 last time? Okay, all right. So back to where we were. We're doing example 2 on page 147. Chapter 4 is vector spaces. 4.1 is vectors in R superscript N. What do we mean by that? We haven't gotten there yet. So here we have the sum of two vectors, u plus v. U is 1, 4, and v is 2, negative 2. The easy way to do this is just add components. First component, 2 plus 1 is 3. Second component is what? Two. 4 minus 2 is 2. There is your resultant, the sum vector. And it is a vector also. Now, I was saying this earlier. The same author, Ron Larson, I've used his book for pre-calculus, algebra, and trig, and his book also for Cal 1, Cal 2, and Cal 3. And in both of those books, in all those sections, he puts vectors in angle brackets. In this book, he puts vectors in parentheses. I don't know why. Same author, and yet he has two different notations. So when you see parentheses in this book, it could be a vector, it could be a point. In this other text, if you see them in parentheses, it's a point. If you see them in angle brackets, it's vector. This, he doesn't make that discrimination. You have to tell by the context. These are vectors. Okay, so let's do this. Vector u is 1 on the x-axis and 4 on the y. So there is vector u. Okay? Vector v is 2 on the x and minus 2 on the y, so it's down this way. Okay, here's vector v. Okay? The sum of these vectors would then either be to take vector v, and last time I put it in a different color, I think I'll do that again. I'll put this, take this one and translate it up here to there, and your resultant vector, I believe last time I did it in baby blue, would be here, which sure enough is 3, 2. 3 on x, 2 on y. Or you could have done vector v, think of that in purple, and then put vector u at the end of it, which is right 1 up 4, and you get right back there again. So there's the parallelogram method of doing it graphically, or this is really the easy way to do it. It's just 3D. That's the sum of those two vectors, u and v. Okay? Let's clear those out of the way. Okay, any questions on it? Okay. And let's do the B one. And in the B one, u is equal to 3, negative 2 and v is equal to negative 3, 2. Okay, I always want to put angle brackets, so when you see them, understand that in this book has to be a parentheses. I almost did it and caught myself just almost too late. What then would be u plus v here? What would that be? 0, 0. You're absolutely right, which has a special name. That's the 0 vector. Okay? It's the only vector we name with a number. We use the number 0 and put an arrow over it. The book bolds it. I have to put the arrow. Okay? Rather bizarre notation, but it's true. So we'll do this. U is 3, negative 2. That's 3 in x, negative 2 in y. So it would be down here. Okay, there's vector u. And I'm going to do my purple for vector v, violet for v. Why don't we do that? That's negative 3, 2. Negative 3 on x, 2 on y. So it would be this direction. Okay? This is vector v. Now the sum of those two vectors, you either put v at the end of u and it takes you right back to the origin, or you put U on the end of V, and it takes you right back to the origin. However you do it, you wind up right back where you started from at a single point with no magnitude and no direction, okay? And that is the zero vector, okay? So that's how that looks graphically. You either add V to U or U to V, either one you do, and you wind up back at the same point, 0, 0. Okay. Now, enough said there. Goodness gracious. Let's do the C part here. Oh, man. I don't know why my eyes are just suddenly itching like crazy, making it hard to see, is 2, 1. I can't write. I wish I could blame that on the eyes, but I just can't write. Okay. 2, 1. And vector V this time actually has another name too. It's the zero vector. 0, 0, which we could have named the zero vector. In the book, it's a bold 0. I have to put 0 with an arrow over it. Okay? Now, what's the sum of those two vectors? U plus V. What's the sum of those two vectors? U plus V. 2, 1. Absolutely. So, and that happens to be the vector U again. Okay? So U plus the zero vector is U, no matter what U is. Okay? Or U are. Okay. It's the additive identity element for vector addition is the zero vector. Okay. I didn't draw it, but we could. 2 and 1, that's right there. And you add to that the zero vector, which is 0, 0, and the sum is also 2, 1. Okay, because you're not adding anything to it. Now, let's go back to the other slide, which I think is this way. Another basic vector operation, first is vector addition, which we've just been batting around. The other basic vector operation is scalar multiplication. I'll just leave an abbreviation there. Scalar multiplication. Well, what a scalar is a number. No magnitude, no direction. Well, it's got a magnitude, a value, but no direction associated with it. Just a number. 7, 43, -5, whatever. Just a number, okay? And you're multiplying that by a vector. That's called scalar multiplication of a vector, okay? To multiply vector V by the scalar C, you multiply each of the components of V by C. Okay. If you have, as we've been doing before, that vector V has components V1, V2, we're in 2 space most of the time now, then this would be the same as C times the vector V1, V2. I can't write, okay? And what it may be suggested to you is exactly what happens. You multiply the constant by okay, sorry. You multiply, it's sort of like you're distributing the C across both components. That's CV1, CV2. You have to multiply everything in the parentheses, both components in the parentheses, by the scalar number c that's outside the parentheses. Okay? And, yeah, I guess they're going to do a representation of that. So let's go to our slide. Now let's use that vector we had there. That was, we're calling vector u. We're not going to use the rest of this, though. Yuck! All right. And we're going to multiply that by a scalar. Pick a number, any number. Pick a number, any number. 10? Is that what you said? It's a bit large because I can't go 10 units on this. 5? Still may be a little large because be 5 times 2 would be 10, and I don't have 10 places there. Say again? Not 1? Is that what you said? 3. Okay, 3 we can do. Okay, so what if we did 3u? Well, that would be 3 times the vector 2, 1. And that would be 6, comma, 3. Yeah, you just give it the new things. My pen keeps touching the board, and when it does, it leaves a mark on the board that I didn't want there. Okay. Goodness gracious. Feel like I can hardly breathe. Well, that then is the vector 6, 3. I can't read my 3, but it's that. That'd be 1, 2, 3, 4, 5, 6. 1, 2, 3, right there. And I'll put this in my purple. 6, 3 right there. Well, look at that. That is a vector in exactly the same direction as u, but it's just 3 times longer than u. Okay? So sure enough, there's 1 length, 2 lengths, 3 lengths, 3 times the length of u. Now, what if that scalar was a minus number, like minus 2? I probably should do this in a different color. Let's do this in the Carolina blue. Minus 2 times 2, 1. That would be minus 4, comma, minus 2. Okay, that would be minus 4 on the x and minus 2 on the y. It would be down here. Goodness, I can't get my eyes to focus. I've been having some problems with my second cataract. I had one removed more than 9 years ago, and now the second one is giving me problems. That's probably part of what all of this is. The headache and everything else is after teaching from 8:30 until now, solid, my eyes are just getting so incredibly tired. But this will be, but notice, well, what happened to my color? Okay. There is the vector minus 2u. It's in the same, along the same line as u and 3u, but it's in the opposite direction of u or 3u. It's in this direction. So there's a minus 2u. Okay? And you see, here's the length minus u, and there's another length minus u, which makes it minus 2. Okay. Does that make sense? Okay? So that's the second operation. Now, related to that one would be, what do we mean by minus u? Let's pick another color for that. How about the red? Minus u would then be doing minus 1 times 2, 1, which would be minus 2, comma, minus 1. Okay? So that would be minus 2, minus 1. That would be right here. Okay? It's exactly the same length as u, but just going in the opposite direction. So that's the negative of u. It's just a scalar multiple. It's just a scalar multiple is a minus 1. Okay? Minus changes its direction. 1 leaves the magnitude the same, but it's in the opposite direction. So it's exactly the mirror image across the origin of the original vector u. That's minus u. Okay? Now, it's also called the negative of u. Now, what that leads to is our ability to subtract vectors. Because if you had u minus v, vector u minus vector v, do it just like you do sine numbers. Just like sine numbers, that would be vector u, add to that the opposite of vector v. That's how we do sine numbers. 3 minus a minus 5 would be 3 plus a positive 5, which would be 8. Same thing here, u plus a minus v would be u plus whatever v was. Now, we don't have a v on the board now, so come up with some dimensions for v. Make up some dimensions for v. X component. Make up a number for v. X component. 2 would be fine. Y component. 6. Okay, we'll go with 2, 6. Okay, so we're going to do u minus v, which would be u was 2, 1, minus v is 2, 6, and that would be, now again, using component notation, the way to go on this. 2 minus 2 would be 0. 1 minus 6 would be negative 5. So there would be the sum of those two. So let me put v, let's see, what color can v be? Let's make v green. Okay, so v is going to be green. That's 2, 6, 2 in x and 6 in y. 2, 4, 6, I think it is. So there is the vector v. Okay, there's the vector u. And if you're subtracting v from u, what that is taking u and adding the negative of v. Well, the negative of v would be down here. This is negative v. Okay? And if you're adding to u negative v, that means you go down to here. Okay? That's not a very straight line, but I'm having trouble with lines today. That's u plus negative v, and here would be the sum. Let's see, what color do we want to put the sum? I believe we're doing Carolina blue, so let's do that. And there would be the sum vector. What do we get? 0 minus 5, and that's exactly 0 minus 5. Okay? Now, what they suggest, if you do u minus v, they say put them as co-initial vectors, and then go from the end of v to the end of u, and that would give you the same blue vector here, 0, negative 5. And sure enough, that's it. Do I use parallelogram method for adding or subtracting vectors? No. It might be helpful just to make sure you're in the right ballpark, but in general, component notation is so much easier. So incredibly much easier. So even if you did this way, this would then be, I'm going to go back to black here. This would be U, which is 2, 1. Sorry, this thing keeps flopping on me. Plus a negative V. Well, negative V would be a negative 2, negative 6. And when you add those two together, you sure enough get 0, negative 5. Which is exactly what we got here and everywhere that we did it. 0, negative 5. So a couple different ways to do vector subtraction. Either just subtract the components, that's easy, or add the negative of the second vector, that's pretty easy, or you can do the parallelogram method, which is a lot more difficult to draw and get it precise, but you can do it if you want to. Okay. And I guess the one I didn't, yeah, I think I did, we talked about it. All right, so let's do example 3. I think we'll go back, well, they do it here, so let me just clear the screen here. Wait a minute, have we just gone over? We have, haven't we? Oh, sorry about that. I'm really sorry about it because I've got so much stuff I've got to do in my 30-minute lunch break. I can't possibly get it all done, so anyway. Homework exercises here. Let me first, man, there it is. Take off that. Okay. Homework exercises here. Let me just give you, you can do number 1, it's at calcchat.com. You can do 3 or 5, they're both at calcchat.com. Either 7 or 9, they're both at calcchat.com. Think you can do any of the odds 11 through 15, they're all at calcchat.com. Think you can do 17, it's at calcchat.com. And then when do they go up to 3? Yeah, we'll hold off there and pick up the rest of those next time. Next time is our last class. We'll get as far as we can. We should be able, I hope, to finish 4.1 and get into 4.2. But I don't know. We'll see what we can do. I don't know if we'll have enough to do another test. If so, I'll try to have one ready for you. If not, chapter 3 test will be your final. Okay?
So you're saying that basically all tests are due Thursday, except for that last one you gave us. That's
yeah. All the ones before that are already past due. This last one I gave you, yeah, you don't have to turn it in Thursday. If you do, I'll get it back to you by the time you turn in the final, if we have a final. If we don't have a test on chapter 4, you can still work on that into the next week. Yeah. So, yeah, no sweat there, because if we do anything in 4, it's going to be very short. I have a feeling we won't do anything, because we just haven't covered enough material. We could do a few vector additions, subtractions, negations and stuff, but that's all we've done so far. So, so I think we'll just go with that, but we'll see. All right, any other questions? All right, let me close this out, because